There's a star so massive that if you placed it where our sun is, its surface would reach beyond Jupiter's orbit. Everything you know about stars, every image you've seen, every comparison you've made, none of it prepares you for this monster. Meet Scuti, a hypergiant star located 7,000 light-years from Earth in the constellation Scutum. To understand just how impossible this object is, we need to start with something familiar: our own sun. Our sun is already unimaginably large. You could fit 1 million Earths inside it. It's the anchor of our entire solar system. But compared to Scuti, our sun is microscopic. And we're about to show you exactly what that means. For most of human history, we thought all stars were roughly the same size, just distant points of light. It wasn't until the early 1900s that astronomers realized stars come in wildly different masses and sizes. They developed a classification system. Main sequence stars like our sun, giants, supergiants, and then hypergiants. Hypergiants are the rarest class. In our entire galaxy of 400 billion stars, we've only confirmed about a dozen. They represent the absolute upper limit of how large a star can physically become before it tears itself apart. Scuti was discovered in 1860 by astronomers at the Bonn Observatory during a routine stellar survey. For over a century, it was just another faint red star in the catalog. Nothing special. Just star number BD-184777. Then in 2013, astronomers measured its actual size using interferometry, combining light from multiple telescopes. The number they got back didn't make sense. They checked their instruments, recalculated. The result was the same. Scuti's radius is approximately 1.2 billion kilometers. That's 750 times larger than our sun. Let that sink in. 750 suns, lined up side by side, would equal the diameter of Scuti. If you could travel at the speed of light, it would take you almost 3 hours just to go from one side to the other. Here's where it gets truly mind-bending. Let's do some impossible comparisons to understand this scale. Imagine you're standing on Earth, looking up at our sun. Now replace the sun with Scuti positioned at the exact same distance. The star would appear 70 times larger in the sky. It wouldn't be a disk. It would be a wall of fire consuming half the visible sky. But let's actually place Scuti where our sun is and see what happens to our solar system. Mercury, the closest planet, completely vaporized. It would be deep inside the star's outer atmosphere. Venus, gone. Earth, gone. Mars, gone. All of them consumed by the star's expanding outer layers. The asteroid belt between Mars and Jupiter, inside the star, millions of kilometers inside. Jupiter, the largest planet in our solar system, 60 times smaller than Scuti, barely at the edge of the photosphere. Saturn and its magnificent rings would be grazing the outer atmosphere. This is where the star's surface would roughly end. Everything inward from Saturn's orbit would be inside Scuti. The entire inner solar system erased. Now here's the crazy part. Despite being 750 times wider than the sun, Scuti is only 30 times more massive. How is that possible? The answer is density, or rather, the complete lack of it. Scuti is so enormously inflated that its outer atmosphere is almost a vacuum. Thinner than any vacuum we can create on Earth. If you could scoop up a cubic meter of material from near the surface, it would weigh less than the air you're breathing right now. This is a star in its death throes. It has burned through its hydrogen fuel and is now fusing heavier elements in its core. Each fusion stage releases less energy and lasts for a shorter time. Helium fusion, carbon fusion, neon, oxygen, silicon. The core is desperately trying to hold the star together through fusion pressure, while gravity is crushing inward. The result is this massive, unstable envelope of gas barely held together by gravity. A star literally tearing itself apart. Scuti is also a variable star. Its brightness changes over time. Sometimes it dims, sometimes it brightens. It's pulsating. These pulsations are the star breathing. expanding and contracting as internal pressure waves ripple through its enormous body. During these pulsations, the star's radius can change by hundreds of millions of kilometers over the course of months. Imagine an object so large that it can expand by a distance greater than Earth's orbit to the Sun just from a stellar hiccup. But Scuti isn't even the largest star we found. There are others. Stephenson 2-18, WOHG 64. Each of these hypergiants challenges our measurements. Their edges are so diffuse, we can't precisely define where they end. We're looking at stars where the concept of a surface becomes meaningless. They just gradually fade into space. The difficulty in measuring them comes from their enormous distance and the fact that they're shrouded in dust they've ejected. Scuti has already lost several solar masses of material through stellar winds, gas streaming off its surface into space. This ejected material forms shells and clouds around the star, making it look even larger and more chaotic. What's happening inside these stars is even more extreme. The core temperature exceeds 1 billion degrees Kelvin. At these temperatures, nuclear reactions happen so fast that the star burns through millions of years of fuel in mere thousands. The core is now crushing silicon into iron, the last element that can be fused before the process becomes energy negative. Once iron fills the core, fusion stops. There's no outward pressure, nothing to hold the star up against gravity. And then, collapse. In less than 1 second, the core implodes. The outer layers follow. This is how supernovae begin. Scuti is living on borrowed time. It could explode tomorrow. It could explode 100,000 years from now. We don't know. When it does go supernova, the explosion will be visible from Earth in broad daylight, a new star appearing in the sky. For weeks, possibly months, it will outshine every star in the night sky except our sun. Ancient humans would have called it an omen. The explosion will release more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. And from that explosion, something incredible happens. The intense heat and pressure forge new elements. Every atom of gold, silver, platinum, uranium in the universe, all of it comes from supernova explosions like this. The calcium in your bones, the iron in your blood, the oxygen you breathe, all forged inside dying stars. Scuti and stars like it are the universe's element factories. Without them, planets like Earth couldn't exist. We are literally made of star stuff. Atoms forged in the cores of hypergiants billions of years ago. After the supernova, what remains of Scuti will collapse into either a neutron star or a black hole. A neutron star would compress 30 solar masses into a sphere just 20 kilometers across. Density beyond comprehension. Or if enough mass remains, it could form a black hole, a point of infinite density where physics as we know it breaks down. Either way, the hypergiant is gone. The monster that once dwarfed our solar system reduced to a cosmic graveyard. So why do stars like Scuti exist at all? Why does the universe allow objects this impossibly large? It comes down to the star's initial mass. Scuti started its life as a massive star, perhaps 30 to 40 solar masses. More mass means stronger gravity. Stronger gravity means higher core temperatures. Higher temperatures mean faster fusion. These stars live fast and die young. While our sun will burn for 10 billion years, Scuti will last only 10 million, 1,000 times shorter lifespan, but 1,000 times more spectacular. These are the rock stars of the cosmos. We're fortunate to study these objects now. In cosmic terms, hypergiants exist for the blink of an eye. Every hypergiant we observe is a snapshot of stellar death, a brief moment before the most energetic explosion in the universe. Current research is focused on understanding exactly when these stars will explode and what triggers the final collapse. Advanced computer simulations are modeling the complex physics inside these dying giants. Turbulence, convection, rotation. New telescopes like the James Webb Space Telescope can peer through the dust surrounding these stars to see their cores. We're discovering that hypergiants don't just explode. They have complex pre-supernova behavior we're only beginning to understand. Some eject massive amounts of material years before the final explosion. Others seem to have false starts, failed supernovae. Understanding these stars helps us understand our own cosmic origins. and the cycle of matter in the universe. It also helps us predict what will happen to other massive stars in our galaxy, and when we might witness the next supernova. The last supernova visible to the naked eye from Earth was in 1604, over 400 years ago. Statistically, we're overdue. Somewhere in our galaxy, a hypergiant is preparing to explode. It could be Betelgeuse, or Scuti. When it happens, it will be one of the most significant astronomical events in human history, a cosmic spectacle watched by billions. Scuti reminds us that the universe operates on scales our minds weren't built to comprehend. A star so large that our entire solar system would fit comfortably inside it. And yet, it's just one of billions. These cosmic monsters live brief, violent lives, then seed the universe with the elements needed for planets and life. Every gold ring, every iron tool, every breath you take. A gift from dying stars like Scuti. So the next time you look up at the night sky, remember, those tiny points of light include objects larger than anything you can imagine. What other cosmic extremes are out there waiting to be discovered? What other impossible objects exist beyond our current understanding? If this changed how you see the universe, consider subscribing. We explore the strangest phenomena in space every week. Next time, we're investigating the star that refuses to explode, Betelgeuse, and the mystery of why it's dimming. Thanks for watching, and remember, you're made of stars.